So when we look at the table, which was in Appendix A, but this is what this looks like. So hopefully you have this out so you can refer to it. So again, what we want to do is we want to find the probability that 0 is less than or equal to z is less than or equal to 1.37 for the standard distribution. So we can draw the picture so we can see what we're talking about. We're seeing that little area. So to figure this out, we want to see where 1.37 is falling on this chart. So we will go down this side until we get to 1.3, and then we move over until we get to 0.7, and there's that block right there, and it equals 0.4147. So we're moving down and across. So the 1.3, so you see that it goes down, and it'll go down. There's the z table goes all the way to the 3.4 right there, and so you'll be able to figure it out up to that. But then again, here we go. It's 1.3 across to 0.7. There it is, 0.4147. So that's your answer, is 0.4147. Okay, let's do it again. Okay, so now it's a little different. We're finding the probability that 0.61 is less than or equal to z is less than or equal to 2.04. So what does that look like? Let's draw the picture. So you see it here in the picture, and that's what we're looking at. We're looking at to see that what is the point that would the z would fall within, the 0.61 and the 2.04. So we would go to our handy dandy chart again. And so we want to look up the figures for 2.04 and 0.61. And we want the area in the middle of that, in that shaded area. So we're going to subtract those numbers that we find. So again, look at this. 0.61, 0.6, over to 1, 0.2291, and then 2.04. Oh, we need our other sheet, right? 2.04, we go across, 0.4793, we subtract. So the probability of the z is 0.2502. So here's another one. Let's see if we can. There was 2 examples. Now we want to say that z is less than 0.75. So again, if we drew this, then you got the region all the way from 0.75 all the way to the left, right? Does that make sense where those are falling? Because if we count the mean as 0, then that's that midpoint. That's that midpoint. And so there would be our 0, because remember we're talking about that's our given, is that it's 0. And we want to go from 0.75 all the way to the other side. But we can think about the fact that what was the amount between right here and right here? 0.5, right? So we don't need to worry about that portion. All we really need to know is this portion right here when we look at the normal probability distribution table, or the Z table, and we would add that 0.5 that's giving you the amount from the mean to the left, and then adding on the 0.75. And again, we find the 0.75 again. We look at our chart, right? 0.75, 0.7, ooh, 0.5. Okay, 0.2734. And so when we add those two together, then we know that the probability is 0.7734 on that one. So then we have another one. So we're just getting the different types in different areas of your graph. See, in this one, we've got this little section right here to the left, and we're looking at negative numbers, right? Because the numbers to that left side of the mean are going to be negative. And so we want to find out what it's going to look like. So we want to look at the score for 2.59 and for 1.1. But we want to take into consideration the fact that they are negative numbers. So that's why when we look at the chart, we just use the positive number. So it's still the same. If you did 2.59, it's 0.4952. And if you looked at 1.1, it would be 0.3643. So your answer would be 0.1309. Okay, so remember, we are looking at points. This is a standard normal distribution. So the mean is 0 and the standard deviation is 1. And that's why these work, is because we do them in that way. So we are going to look at a little bit different way to do it now. Suppose we're given a value x from any distribution with the mean and standard deviation. If we want to measure how far x is from the central value, then we're going to compute the difference. So x minus the mean. You've seen this before. We've done a little bit of this, which will be negative if x is smaller than the mean and positive if x is larger than the mean. So that's something to keep in mind. Also, that's something if in your answers, if you know what it's supposed to be, then you'll be able to figure out, oh, is it negative or is it positive? Okay. So, for example, we would look at a typical spread that we have represented by the standard deviation. So we're going to divide the standard deviation. We're going to divide the difference of x minus the mean by the standard deviation. Okay, and then we call this the z-score associated to x. So the z-score is equal to the number of standard deviations x is from the mean, along with a plus or minus sign indicating whether it's larger or smaller than the mean. So we want to know whether it's on this side of the mean or if it's on that side of the mean, and we will do that by using positive or negative. So if you look at this nice little graph here and you look at where these are all falling, then you can see based on that where the z-score would be based on either the standard distribution or this one on those numbers where the mean is not going to be that 0 and the standard deviation of 1. So we're looking again, this is how we would look at these formulas. So we are going to look, so make sure you have those written down. Make sure you have those. And we will look at, again, we're going to go back and look at a standard normal distribution. A general normal distribution. The mean is not 0 and the standard deviation is not 1. We did those, right? Now we're going to go to where that's not the case. So suppose that x is a random variable from a normal distribution with mean of 3 and standard deviation of 6. So we want to find what that x value is. Okay, we want to find the x value. So we want to look at this formula. We are going to say, and we have that up here, right there, z is equal to x minus the mean over the standard deviation. So we're going to do that again, and we're going to say z is equal to x minus the mean over the standard deviation. Okay, so hopefully you can see that. So that's what we're going to do. We're going to say that from our little diagram, and we have that we have z is equal to x minus 3, x, which was 0, because that's the point right there, minus 3, which was your mean, right, divided by the standard deviation, which was 6. Okay, so we're doing that side first, right? We're figuring out that side. So when we subtract that out, we get negative 3 over 6, which is negative a half, which is also negative 0.5, right? Because we're going to look at it with the 0.5, the decimal places. And then when we look at the x being 5, then we have z is equal to, so we're plugging it in again to that formula, the z is equal to x minus the mean over the standard deviation. So it's 5 minus 3 over 6, right? So we've got 5 minus 3 over 6, which gives us 2/6, which is 1/3, and we can use the calculator, 1 divided by 3, or maybe if some of you remember from way back in your math, 1/3 is equal to 0.33 approximately. Okay, so then we have the probability, and it's approximately equal to, the one for the x is approximately equal to negative 0.5 is less than z is less than 0.33. So now, wait a minute, we see that z again, right? Because here, this one is an x, but we're converting it. So we can use the chart that we used before, yes, to find the z. So we will say the probability of 0 is less than x is less than 5 is approximately equal to, and we'll use those numbers we found, which was negative 0.5 is less than z is less than 0.33, and then we will just use our little chart and find 0.5. Find 0.5. Okay, which is just 0.50, which is right there, which is 0.1915. And then we're on both sides of the mean, and so we have plus your 0.33. Remember, when we do this, we drop the negative. We're adding those together. We want both sides, and so we're getting the z being 3.3208. And we have another example. So we are looking at the probability for a general normal distribution. In this one, we're going to say that the mean is negative 4.2 and the standard deviation is 3.1. Look at where it's located. We also want to look at the probability. We're going to use the formula to find that point, that z, which ends up being 1.68. When we look at that, we are in this, remember how we added 0.5 back before that, and we had like, it was like all of the one side and just a little portion of the other, and so we wanted to get that amount, which was like 0.75. This one is a little different because we are going to subtract. And why are we going to subtract? I'm going to get back to that formula, that problem, in just a minute. Okay, so we're going to subtract because that little part right here is not shaded where you see on the in the textbook. We want the part that's shaded. So we're gonna subtract 0.5 from the z-score amount that we get. So to find the area. So we know that the area is 0.5 minus the 0.4535, which we got off the chart going 1.68, 0.4535, and that gave us the answer of 0.0465. We can do this, right? One more, another one. Going through the same amount again, we are looking at a mean of 105.3 and a standard deviation of 21.7, and we want x to be less than or equal to 100. So we have this probability. We do our division because we are looking at z is equal to x minus the mean over the standard deviation, right? So we get negative 0.24. We put that into the probability formula. This one, see where it is? See how when you graphed it, remember that's why it's so nice to see the graph. All of that right side is shaded, but we just have that little bitty portion on the left. So we're going to add the 0.5 there. So it's going to be 0.0948 plus the 0.5, which is going to give us the 0.5948. So we are going to look at this example. We're going to look at the SAT scores, and we're going to look at the percentage of scores that fall between 545 and 655. So raise that probability again, right? So we're looking at the probability on this one of 545 being less than or equal to x, and x being less than or equal to 655. So we set up the formula again. Again, we have that x, the x minus the mean, and we are going to say 545 minus 528, and that is going to give us, divided by the 120, and that's going to give us the z, and we're going to have the probability for that, and we can figure out the percentage. So this is the percentage of scores that fall between those two numbers. So we find that the z-score, the 1.06 and the 0.14, and then we just find the percent from that. And so then we're going to estimate the percentage of scores that are at least 675. So that portion from right there all the way to there And so when you figure that out, that's 10.93. And that makes sense because that's a smaller area than the area that you get from the part A of the problem. So a little on percentiles. We are going to look at the P or X percentile. So we might want to look for the percentiles for the standard normal distribution. So we look at the 80th percentile and the 17th in this case. When we look at the 80th percentile, we're looking at this. As you can see, this graph that's right here, and that's the area for 0.8. And then we want to look at computing that 80th percentile. So we want to say that the 80th percentile corresponds to a z-score of about 0.84. And we got that from looking again at your Appendix A, right? Again, we have our Appendix A and looking at where 0.3 would fall. And in this case, this is a little bit different because instead of starting with these, the Z, we're trying to find the percentile. We're looking at the area under the percentile. So we're doing this kind of opposite. So instead of going 0.3 and saying 0.1179, now we're going to look into the table and we're going to look to see what comes closer to 0.3. And so when I'm looking at it, I see that it's over 0.8. And then I go across, but it's still between 0.04 and 0.05, so it's kind of not either one. So we can kind of guess a value between the two. But, basically it's, it could be halfway between. It could be 0.845 maybe, which ends up being 0.84 or 0.85. So it's somewhere out around there. Remember, we're kind of estimating it, so it's not going to be exact science, but it's going to be close enough. So, and when your answers, when you get those on there, again, looking at them, and with all graphs, there's going to be some estimation, and that's why I go back in and look at your exercises and see, well, it's just a little off, and I can see where you would, say that, so it would be all right. So if we wanted to look at the 17th percentile here, then we want to find the value of Z for that area, because now we're looking at area. So we want to say it's between, look at this, 0.5 and 0.17. That's the area that we are, the desired Z-score, which is 0 in this case. We're going back to the 0. So we say 0.5 minus 0.17, which would be 0.33. And if we look at 0.33 in the graph, I'm looking at the difference is 0.95 and 0.96, so somewhere around there. And so then we would say that it's negative 0.95 would be your Z-score on that one. But we would say it's on that other side, so we're looking at a negative in this case. So if we want to, here's another formula that you can use. X is equal to the mean plus z times the standard deviation. And what we want to think about and what we see when we have these graphs is that x is greater than the mean when z is positive, and x is less than the mean when z is negative. So that will help you to also determine whether you're going to have a positive or a negative, like when we found up here that this was negative on the 17th percentile, but it was positive on the 80th percentile. Okay, so you have to look at the mean and you have to say, okay, what does the mean look like and whether it's a negative or a positive. And that's just one of those standard things that that you would look at with that. So if we have another example, we're looking at percentiles again. We're looking at a normal distribution with mean of 4 and a standard deviation of 3. And we want to figure the 35th percentile on that. Again, we've got our little sketch. And look at where in figure 3.31 that this area falls. Remember that we've got this half is 0.5, right? It's always 0.5, whether the mean is 0 or whether they're in these cases where the mean is not. And so we're going to say 0.5 minus 0.35 and get that 0.15. And then we would find the z-score of, so if I go to 0.15, we will see about, let's see, 0.5, yeah, 3.9, 0.517, the same, okay? But we look at also the standard deviation, and again, we're just doing the same, 0.5 plus the 0.2673. We've done this formula. And so then we can see where that would fall. And we're almost done with 3.4. Yeah, we can get back to it. So hopefully those examples will help you with the different formulas. In the different, trying to figure them out, I would continue to look back at these examples in the textbook, because they can help you a lot, and definitely rely on these charts, because these are going to give you the answers you need just by looking it up in the chart. Another one, we look at the percentiles in the SAT, and that is just the same as the question before. And it also had that third part, because remember we were looking at just the first two parts of the SAT score that falls at the 75th and at the 40. And then we say, well, so to what percentile does a score of 600 correspond? So how does that make sense? So we change that x. We know that x is less than or equal to 600. So we want to find the z. So we say the mean minus the x minus the mean divided by the standard deviation. Yes, and that's how we get that. It is the 0.5 again right here, plus what we find for 0.6, which is 0.2257. Right there. Okay, and then we would say that it would be 0.6. So wow, that was a lot. that was a whole lot. It's just a matter of working through them, looking at examples, continuing to work through examples, making sure you're looking at what it's saying for the standard deviation and the mean, and that will determine what kind of problem you're doing. Whether it says X or whether it says Z, and that'll determine what part of the chart that you're looking at as well. So just pay particular attention. Just make sure you read the problem. I think another big thing, and I cannot stress this enough, is to draw the picture. If the picture is not there in your problem, to draw it out, and so you can kind of get an idea. And remember, we saw that that 1/2 of it is 0.5. So if it's just a little bit more than that, we know it's going to at least be 0.5, and we're going to add. If it's just that little portion on this other side and we know it's 0.5 here, then we're going to subtract because we're looking for the difference, okay, for those sections. So the last section of this chapter is estimating the mean. We also will call this, what we are looking at is confidence intervals. So we are trying to see how confident we are in our data, how confident we are that the probability of that number is actually going to be falling within that section that we're looking at. So in this section, we are looking at sample sizes and sample means and sample standard deviations, as opposed to the population mean and the population standard deviation, which is that typical when we had the U symbol and then the standard deviation symbol. So we are going to have N be our sample size, our random sample size, and X bar is the mean of that sample size. So instead of looking at all of them, we're looking at a sample. Again, if you see a problem and it specifically says we're looking at the sample, then you know you are looking at the formula related to the sample size as opposed to the population. So here's a theorem, theorem 5.1. It's a theorem. N is independent random samples from a population with a population mean of the regular mean and the regular standard deviation. So we are going to say, number one, as part of this theorem, when all possible samples of size n are considered, the distribution of sample means, X bar, has the mean and standard deviation is divided, the standard deviation divided by the square root of the size. If the original population had a normal distribution, then the sample, we are going to assume that the sample means does as well. Part of this is also the central limit theorem, which states that as n increases, the distribution of X bar over all possible samples of n approaches a normal distribution. That's just something to know. I'm not asking you to memorize any of that, but it's just something that that's used to describe this section of confidence intervals. We also look at, when we talk about n, we usually say that n is greater than or equal to 30. and we use another table, or use the table to estimate our probabilities as well. So we're going to get to that again, but let's talk a little bit about how we're going to get there. So these are some pictures of the distribution of the mean of the sample population, or the X bar. So this is the sample. So it's a portion of, because you can't always get, so let me kind of go back on that. When we talk about a population, we talk about every single possible part or whole, every single possible data point. So that would mean that you would have to, if you were going to find the mean and standard deviation of a group of data points, they would have to reflect every single one of the points. So if you had a population of, for example, 100,000 people, you would have to have 100,000 data points, because that represents the population. But what we're saying is that we can kind of get it with using the sample instead of the population. But with that, because we're taking a smaller portion of that entire population, we want to know how sure or confident we are that that portion that we've taken from the population is actually going to be a representative sample of everybody. So we go back to, like, for example, I love this one about 3 out of 4 dentists surveyed think, whatever, blah, 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 this type of toothpaste is, the best, whatever. 3 out of 4, okay? Is the population 4? And if it was, that's not all the dentists. And so we would want to know that, so if the population is this size, and you're saying 3 out of 4, which seems like it would be little bitty, are we really confident in saying that the results that we are getting actually are representative of the entire people in that whole population? Okay, so, we'll see. So I like these graphs right here, and you can kind of see that depending on the size of your sample, what your graph is going to look like. So it looks more like what we want it to look like as the sample size gets bigger, right? It looks more like our normal curve as we get higher. So we want to sample as much as possible because we want it to be as accurate as possible, our results. And if they're not, then we can only really kind of give an educated guess, if that makes sense, kind of an educated as best as we can. So when we get into the confidence intervals, we are going to use that theorem 5.1. And we begin by computing an interval about the mean that will contain the value of X bar, which is the mean of the sample, okay, approximately 90% of the time. Now we're saying approximately, remember, because we're getting as close as we can, and we don't have the entire population, right? So we only have a sample of that population. So we look at it. We first want to find the z-score that will correspond to the total area that we're talking about, which is 90%. So if you see this graph, the curve right here, that's kind of the area of 0.9. So we also look at how much is on each side of that mean. So if we divide 0.9 by 2, we're going to get that 0.5. So if we're looking at how confident we are, again, we're going to look at the z-scores. We are going to estimate the z-score that corresponds to a probability or area of 0.45. So that is that portion. So we look on our little table, right? So because 0.4495, right there, 1.64, right? 1.645. So the distribution of sample means X bar has the mean of the population mean, and the standard deviation is the standard deviation divided by the square root of n. Remember, the square root is not squared, it's the square root. So it's a different formula that you use. Instead of, if you had n squared, that would be like, for example, 9 times 9, which would give you 81. But when you do the square root of 9, you don't get 81. And if let's see, 9 square root, you actually get 3. So the square root of 9 is 3. We are going to use this formula for to find the answer for that. And it will be z is equal to x bar. X bar is the mean of the sample minus the mean of the population divided by the standard deviation divided by the square root of n. So we're going to assume again that the sample size is greater than 30. Because if we have a sample size that's smaller, it's unless our population is pretty small, that's just a pretty good standard to use. So we already saw that each side, so the side on this side of the mean and the other side of the mean is 1.645. So we're going to calculate this answer based on knowing that the z-score is between negative 1.645 and positive 1.645, because you can see that on the picture that we drew right there, right? Okay, so we plug in all the numbers that we have, and we can split them up so each side has parts of the formula. And kind of the reason why we did some of that fundamental section is to figure out how to make sure that we do that and do that correctly. And so that's where we figure this out. And it can be either way. The two formulas written, so just as you're doing the formulas, that's how you would figure that out. When we are looking at the sample standard deviation, it's going to be a little bit different than our regular standard deviation that we talked about before. And with that, we're saying n minus 1 for our sample instead of n. Okay, because it makes it a little bit more, remember it's an estimate. So, instead of having, x minus the mean, we're having x minus the mean of the sample. And so that's why we're going with the n minus 1. Again, too, if you see this really daunting one, but that's when we have the frequency, and you can do the calculation for that as well. And then you'd have the standard deviation to help you fill out the problem. So if we look at the confidence intervals and the margin of error, for different means, then you have the calculations for that and just plug in the numbers as they go along to see how confident you are that 90% in this example of you have a 90% confidence interval, that there's 10% 10% probability that the true mean will lie outside, but 90% that it's going to fall within, okay, your sample size. Because remember, it's not the whole, but it's a portion. Now we can take something less than 95%, 90%. We can take something higher than 90%, and we could get to 95, because we want to be really confident about that when we're saying that our number is falling within a certain range, and we don't want to have very much error in that. We want to, and I think probably in a lot of your misleading graphs, it'll have that, the confidence interval and the margin of error. That's to say they're off. Remember the thing, plus or minus 3%, plus or minus 5%, that kind of thing. That's where this comes from, and that's what we're figuring out. So, and this one, kind of cool, the shoulder heights of 352 African elephants of mixed genders and ages in a national park. They got the average shoulder height of the sample, which was 6.37, and the standard deviation. And so we want to find the margin of error of that 95% confidence level. So again, we're using that Z. We're dividing the area, 0.95 divided by 2, and we get the 0.475. When we do that, look again at our Z table and look for 0.475. Which is 1.96. So the margin of error would be that 1.96 times your 0.82, because that was the standard deviation, right? Divided by the square root of the sample size, which was 352. And so when you figure that out, then you get 0.9. So we're looking at the margin of error for that. If we had a smaller confidence interval, then we would see different numbers, and we would say we weren't as confident, or we would have a greater margin of error for those answers. And I have another example here. Head impacts in college football. That's a big thing. This is from a survey from a neurosurgery, and they looked at the impact for different players, and so they looked at the difference in the mean between the wide receivers and the defensive backs. So here's another way where we apply it. Okay, so we applied it up here when we were talking about the elephants and the shoulder heights. You probably won't ever use that, but hey, if you're a scientist, or if you're maybe a coach, you might want to know the confidence interval or the mean head impact between wide receivers and defensive backs. And so we look at 99% confidence here. So it's greater than the 95 we saw before and the 90. Again, the 99% confidence, you're dividing that by 2, getting the 0.495. Then we, again, look at our little handy-dandy chart. 0.495 is on the next page. And it looks like 2.54, 2.55, somewhere around there. Okay, so, and then we figure it out based on having that. So we get the 2.19 grams. That's the sample size of the wide receivers. And then you're subtracting that sample standard deviation, which they gave you, divided by the square root of the sample, and that was the 2503. We figure out the math and we get 22.28. We do the same thing again when we look at defensive backs and we see the difference. So we have 22.28 grams for the mean head impact for wide receivers, and the confidence interval for the mean weight head impact for defensive backs is 21.07. So based on that, then we could say that the head impact for wide receivers, the confidence intervals, and the mean is greater for wide receivers than defensive backs. It's not that much, but it's there. So you can see the difference. Scottish militiamen from over 150 years ago, we got their chest sizes. I don't know how, why. But anyway, we do. And we want a 99.5 confidence interval that the mean chest size for the Scottish militiamen for that period. We want to know that. What is that? So in here, again, we have frequency. So instead of just saying the 33, we have to say the 33 times the 3, the 34 times the 18, plus the 35 times the, and on and on and on, right? Divided by the sample size, 5738, and we get 39.83. So then, because now we need to do the sample standard deviation, we will go through that whole formula again. Remember, 3 times 33, which was our first number up here, right? And this was, we got our mean, 39.83. So that's where we're subtracting that, squaring it. And remember, when we square it, we get a positive number. Again, with the sample standard deviation, we're subtracting 1, because remember, it's an estimate. So we're trying to get a little bit closer. So that's what our mathematicians have decided, that when we have the sample standard deviation, we're going to say n minus 1. So we get 2.05. And then the next step would be to find that the z-score corresponding to that area, 0.995, divided by 2, 0.4975. We get 2.81. Again, if we look at that, we plug in all of that, and we find out that the mean chest size of Scottish militiamen at that time was between 39.75 inches and 39.91 inches. Again, does that mean anything for us now? It might mean something for scientists, for archaeologists that are looking at that data, but you can always put in your own data points and figure out the answers in that way. So that ends chapter 3. Then you start with the exercises. So you can go down, and we go back into, and we start with the frequency and the relative frequency. And as we go down further, we get into those confidence intervals like we just talked about. Some of these will say rounded to decimal places. Please make sure that you do that. If you have any questions, let me know. If you're coming up with any problems and you say, I did this right and it doesn't say it's right, let me know again too, because I can work it out and work on it. Don't confuse yourself too much. Again, for some reason, either it's a rounding issue or something, but for some of these you're being marked wrong and you shouldn't be. So check on that. don't get too frustrated, please. I'm here for you. We can work one-on-one with tutoring, or I can refer you to someone as well. And yeah, so yay, chapter 3. Next, on to chapter 4. Thank you for listening. I hope you learned something, a little bit about statistics.